Okay, so now we're going to prove this, and we'll do it one statement at a time. So for the first statement, remember that we just wanted to prove that the norm of any vector is always greater than or equal to 0. So let's write it out. Let's just write out the formula and make some observations. So the norm of the vector x, well, I guess we need to have some coordinates for it. So let's say, let me reserve some space off to the side here, just so we have actual coordinates to refer to. Formally within this context, we never said what the coordinates of the vector x were. So let's just say, okay, let x be given by these coordinates, x1, x2. We'll just use the usual naming convention. So that can be our vector x. And I'm just going to carve this space out to separate it from the rest of our work. And I'm going to add something else to that later. But for now, let's just take that to be the vector x. So we can actually write out the norm of x just by using the formula, right? Square each of the coordinates, add them up, and take the square root of the sum. So we'll have x1 squared plus x2 squared, and so on. But you're going to do that with every coordinate all the way up to and including the final term, xn squared. And then we have to take the square root of that. So that is the norm of the vector x. Now, for starters, why, by the way, this is a good time to mention this. Why is it guaranteed that this is going to be defined? Because remember, you can never take the square root of a negative number. So if the inside of the square root ever worked out to be negative, this would be undefined. But I never mentioned that when we went through the definition, and it turns out to never be a problem, right? Because what's inside the square root? You've got something squared plus something else squared, and you just square all the terms. When you square all the, square all the coordinates. And when you square all the coordinates, you're never going to get a negative number back. So you're really just adding up a bunch of numbers that are all guaranteed to be greater than or equal to 0. So let's make that observation. x1 squared, that's greater than or equal to 0. x2 squared, that's going to be greater than or equal to 0. And then including the very last term and all the other terms, they're all the squares of real numbers. So they're guaranteed to be greater than or equal to 0. So that's just why we know for sure that this norm formula always gives you a sensible definition. But how do we know that it's always greater than or equal to 0? Because that's the definition of a square root, right? The square root, by definition, is always greater than or equal to 0 as long as it's defined, which it is guaranteed to be defined because of all the terms being greater than or equal to 0. So that's why we can say that this is greater than or equal to 0. There's not a lot to write down there. It's more just observing the way the formula is built. That's why it's guaranteed to be greater than or equal to 0. These observations we made here, though, are going to come in handy for the second statement when we go to prove that. Remember what the second statement was? Just that the norm of a vector x is equal to 0 if and only if that vector x happens to be the 0 vector. That's the only way its norm can be equal to 0. So, well, how could this ever end up being 0? When is the square root of something equal to 0? Well, it's the square root of something is going to be equal to 0 if the thing inside the square root is equal to 0. But you're adding up a bunch of terms that are all greater than or equal to 0. So if you want to get 0 for that sum, and none of the terms can be negative, well, then none of them can be positive either. They're all going to have to be precisely equal to 0. That's the only way that the square root can end up giving you back the value 0. So what that means is, we could say the following. The norm of the vector x is equal to 0. Just based on the observation we just made, it's equal to 0 if and only if each of the coordinates are equal to 0. x1, x2, all the way up to the very last coordinate. So this part's saying that all the coordinates are equal, and then finally not only are they all equal, but they all are equal to 0. Or in other words, what's the vector in which every coordinate is equal to 0? Well, that's exactly what the 0 vector is, right? The 0 vector is the vector that has the coordinates given by all zeros. So in other words, so let's fill that in. Or in other words, x itself is the 0 vector. Okay, so that's how we can justify the second statement. Really, it comes down to these observations, right? That's why because of the fact that none of these terms can be negative, none of them can be positive either if you want to end up getting, assuming you want to get 0 back for the square root. Right? So the only way that the inside of the square root can be 0 is if each of the individual terms are equal to 0. Because if one of them was positive, well, none of them are allowed to be negative to compensate. So for that reason, they'd all have to be equal to 0. So that's how you can justify the second statement. And the third statement now, we claimed that the norm of k times the vector x is just equal to the absolute value of k times the norm of x. Now, the way you prove that one is just by direct computation. Directly calculate this using the definition of norm. And that's what we're going to do. So for statement 3, we're just going to start by applying the definition of norm to the vector kx. Now, it's going to be helpful to actually write out kx in terms of its coordinates. And that's why this extra space up here will be handy, because if x is the vector x1 up to xn, if these are the coordinates of x, then we can write out the coordinates of kx as follows. Remember how scalar multiplication works? You're just going to multiply each of the coordinates by the scalar k. So we're going to get kx1 for the first coordinate, kx2 for the second coordinate, and by the time we get to the last one, we'll have k times xn. Okay, so that's your that's the definition of k times x. So let's plug it in. Plug this into the definition of norm. So how do you take the norm of a vector? Well, just square all the coordinates, add them up, and take the square root of the result. So we're going to do that to all of these coordinates here. So we're going to get the square root of the square of kx1 plus the square of kx2, and we'll do that for every single term all the way up to the square of kxn. So that's the definition of the norm of kx. But now we can apply properties of exponents to each of these terms, right? K times x1, these are just two numbers multiplied. So if I take the square of the product, I could just put the square on each of those two factors separately. And same for this term here and this term here, all of them. So what it'll look like if you do that is you get the square root. You'll have k squared times x1 squared. That's your first term, just written differently. Your second term, you've got k squared x2 squared. That's the second term if I apply the square to both of the two factors separately. And if I just keep doing that to each of the terms separately, the last one I'll have k squared times xn squared. Okay, so that's what you'll get on the next line. And then now you have n terms, right? 1, 2, all the way up to n is the last one. There's n terms, and they all have a common factor of k squared. So you can factor out the k squared, and that's how this ends up finishing off. So it's the square root of k squared times, well, x1 squared plus x2 squared all the way up to xn squared. And then now we've got the square root of a product. The product of k squared and the sum of the squares of all the coordinates of x. Those are your two factors. There's one factor here and then one factor here. This big sum is the second factor. So the square root of that product can be broken up into the product of two separate square roots. So we can write this as the square root of k squared times the square root of x1 squared plus x2 squared all the way up to your last term, xn squared. Okay, so that's how you can break that square root up. And what's this? The square root of k squared. The square root and the squared cancel, but because the square root is always positive, right? Remember that the square root is by definition always positive. This is actually going to turn into the absolute value of k. And what's this? The square root of x1 squared plus x2 squared all the way down to xn squared. That is just exactly the definition of the norm of x. Right, so we're done. This is how it works out, and our last line is just going to be exactly what we want. It's the absolute value of k. That's the first factor, and then this is just the norm of x multiplied by the norm of the vector x. So that completes the proof for that third statement, and thus the whole theorem. So that is the proof for this theorem here, which consisted of those three statements that we just proved one at a time. Okay, another idea that we can talk about is the idea of a unit vector. So this is another term that you'll want to know. So a vector x, and this applies to vectors in any dimension, is called a unit vector if its length is equal to 1. So to finish the sentence, we'll just say it's a unit vector if the norm of x happens to be equal to 1. And that's what a unit vector is. Okay, and there's a nice way that you can turn any vector, as long as it's non-zero, into a unit vector. And this note is going to tell you how to do it. So here's how it goes. For any non-zero vector x in Rn, you can turn it into a unit vector just by multiplying it by an appropriate scalar. So here's what you'll do if you want to do this. So if I take 1 over the norm of x, and that is guaranteed to be a defined number, right? The only way this wouldn't work is if the denominator were equal to 0. But the norm of a non-zero vector can never be 0. We just proved that. So this is guaranteed to be a positive number if x is a non-zero vector. So that's why this is definitely a sensible fraction. Now, but it's a scalar, right? Because it's a number divided by a number. This is just a real number. It's not a vector. So you can take this as a scalar and multiply it by the vector x now. So you're taking the vector x and you multiply it by 1 over its own length. That's really what's happening. And I'll put brackets around this just to make it a little bit easier to see what is the scalar and what is the vector. But in general, you might not always write those brackets, and that's okay. But I just want to write them this time to make it a bit more clear. So if I take the vector x and multiply it by the scalar consisting of 1 divided by its own length, that's guaranteed to be a unit vector. Let's check why that works. Let's check that. It actually only takes one line to do it. So how would you check it? How do you check that this is guaranteed to be a unit vector if you don't know what the vector x is? Well, let's write down its length and see if we get 1. You might be able to calculate it. In this case, you can. So if we want to show that this is a unit vector, we have to show that its length is equal to 1. So let's write down its length. I'm going to have to do big, tall bars here because there's a lot of notation here. I want to leave myself lots of space. So I've got 1 over the norm of x, and I'm multiplying that scalar by the vector x, and then I'm taking the length of it afterwards. And I want to show that this is equal to 1. That's really what it means to have this be a unit vector. Well, how are we going to do this? It looks maybe a bit harder than it actually is. Because look at this, 1 over the absolute, or not the absolute value, 1 over the magnitude of the vector x, or 1 over the norm of x, this is just a scalar. And, well, property 3 of the theorem we just proved says you could take a scalar and pull it out of a norm, but just put an absolute value sign on it. Okay, well, let's just follow that honestly here. So we'll have the absolute value of 1 over the norm of the vector x. Basically, just think of the 1 over the norm of x. Think of this part in brackets, this scalar, as your k. So this is the absolute value of k multiplied by the norm of x. Okay, well, what about this absolute value? Is it even doing anything? Well, 1 over the magnitude of the vector x. Remember, the norm of x is never negative. It's always positive or maybe equal to 0. But in the case of a non-zero vector, it can never be 0. So the norm of x is already positive. So 1 over the norm of x is also positive. So really, this is just the absolute value of a positive number. The absolute values are doing nothing. So we can just write this as 1 over the norm of x multiplied by the norm of x. So it's just like if you had 1/2 times 2 or 1/3 times 3. Really what happens is they're going to cancel and they just give you back 1. So that's why it's guaranteed to work always. So this is just the verification of that note. If you start with a non-zero vector x and you multiply it by 1 over its own norm, its length is going to become 1, and therefore it's a unit vector. Let's finish this page off with an example of a problem that you might be faced with. So quite often you have a vector. So what does it say? Find a unit vector u. So we're not given u, but we want it to be a unit vector, but it's supposed to have the same direction as this vector v. So how are we going to accomplish that? We need to get a vector that has the same direction as v. In other words, it's got to be a positive scalar multiple of v. Because if it were a negative scalar multiple of v, then it would have the opposite direction. So we want a positive scalar multiple of this vector v. But we want to choose the right multiple so that it ends up having length 1. It ends up being a unit vector in the end. So that's the vector we need to come up with, and this is just some other vector that we're given. Well, it helps to start by figuring out the length of the vector that you're given, this vector v. This is not going to be our answer, but it's just good to know. It's going to help us build our answer, knowing what the length of this vector v is. So we can first calculate the norm of the vector v just in a normal way, right? We've got 3 coordinates, 2, 2, and 1. So we're going to take the square root of 2 squared plus 2 squared plus 1 squared. So what does that give you? 4 plus 4 plus 1, that's going to give you 9. So you get the square root of 9, which is equal to 3. Okay, so this vector has a length 3. So really what we want to do is we want to shrink it. We want to compress it by multiplying by the appropriate positive scalar. And what are we going to multiply it by? Well, this note tells you exactly what you need to multiply it by, right? If you've got a vector, a non-zero vector x, think of this vector here as this vector v that we're given, right? How do you turn it into a unit vector? Just multiply it by 1 over its own length. So if we multiply it by 1 over its own length, which is 3, that's going to turn it into a unit vector. So we can take u. Where do I write? I'll write it down on the next line below just to make sure I have enough room. So we'll just take u to just be 1 over. I'll just write it out in full just so we can see it work out. So this is just the notation I would use in the case of the vector v if I want to apply this trick here to turn it into a unit vector. But I'm doing it to the vector v that we were actually given. So I'm going 1 over the length of v multiplied by the vector v. But the length of v was just 3. So this is just 1 over 3 times the vector v. But the vector v is 2, 2, 1. So this is 1/3 of the vector 2, 2, 1. So, in other words, therefore, our vector u is just going to be 1/3 times 2, 2, 1. Or, in other words, you might prefer to just write it out in terms of its coordinates. You can just write 2/3, 2/3, and 1/3, because that's what happens if you multiply this vector by 1/3, right? You're going to multiply each of the 3 coordinates by 1/3, and you're going to get this. But it is completely reasonable to just write your vector u in this fashion, because this is still the vector you want, right? It just happens to be written as a scalar product of some other vector. But in some cases, you might want to actually know what the coordinates are exactly of the vector u, so you might prefer to write it out this way. But both of these forms are completely valid, so I'm going to put a box around both of them. But in general, you only need one. You don't need to write them both, but I just want to write them both down to show you that they're both valid. But in general, just pick your favorite form.